Hello, thank you for joining us. Welcome to this webinar event. This is one of many of such webinar events that is presented by Texas Instruments Australia as part of its ongoing support for teachers in the classroom. Today's topic, exam preparation for VCE Specialist Mathematics. My name is Brian Lannan. I'm your host for this evening, and your presenters are Raymond Rosen and Peter Flynn. Good evening. What have you got happening for us there, Ray?
Okay, can you see my screen now?
We can indeed. It looks much better than mine.
Okay, all right. Well, welcome everybody to tonight's webinar. My name is Raymond, and tonight we're going to go through a few sort of typical exam type questions on functions and graphs, some complex numbers, some vectors or vector calculus, some velocity time graphs, differential equations, looking at Euler's method, some variable acceleration and projectile motion. Now, I've probably got quite a lot of material here, so we'll get through some of it, and the rest of the files will be distributed to everybody to see. All right, so let's just have a look at some of the questions that I've got here today. So here's a nice little question. Find the maximal domain and range of this function. Now, a lot of students just think, all right, well, let's just find the domain of the sine 3, r sine 3 minus x, which would end up between 2 and 4 inclusive. But that's not going to work because of this pi on 2 here. However, the TI does have a lovely new feature here, which is the domain function. So I'll do this one on a notes page. So I'll open up a notes page, and on the notes page we have to insert a maths box. I presume people have been familiar with a bit of the notes pages by watching some of the other webinars. So what we have to do is we have to insert a maths box. So in this maths box, I'll type in define f1 of x equal to this function. So we'll use the template, the vinculum, and type in 2x. And in the bottom line, a nice little trick here, you can just type on pi, pi on 2, minus, and we'll get the r sine function from the trig template here. So the trig template here is then r sine of 3 minus x. So that's defined my function. Now, one of these nice little features is the domain function. The domain function you can't get from any menu. You could get it from the catalogue or the book. So let's have a little look if we hit the icon for the book. And we'll hit the letter D and scroll up till we see D. So the domain says expression and variable. Again, this is in a maths box. So I'll just type in f1 of x, comma x, and it tells me my domain is 2 not included to 4 included. So that means I can actually evaluate the function at 4. I could actually evaluate the function at 3. But what happens if I try to evaluate the function at 2? It tells me that it's undefined. All right, so we could actually look at the graph of this, this function, and I've pre-prepared this one. So we see that the function has got a vertical asymptote at x equals 2. I've drawn that one in previously using the templates for x equals and made the attributes of that straight line dotted so we can see it's an asymptote. So out of this we can then see that x equals 4 is the end point, and the range is from 8 on pi inclusive up to infinity. All right, so that's one little question about domains where we can use our CAS. And that has been typical sort of questions in multiple choice type questions. All right, so let's have a look at another question we'll look at here. Let's try to sketch this rational function and look at the interesting features of this equation as asymptotes or axial intercepts or any other sort of special features of this function. All right, so let me just type this function in. We'll start it again. So if there's the function f1 of x, let me just clear the screen here. Now, the function f1 of x is defined because I'm going to graph it. But even though I've defined it as that, when I just type in f1 of x, some funny things happen here. So when I type in f1 of x, the x is then cancelled automatically. So it's lost the x. What we can actually do, though, is we can just try to factorise the numerator or factorise the denominator. And these are nice little expressions that we can do. So if we go Menu, Algebra, Fractional Tools, and the Get Numerator or Get Denominator. Okay, so let's try that again. What I want to do now is I want to factor. So we'll go Menu, Algebra, Factor, Menu, Algebra, Menu, Algebra, Fractional Tools, and we'll just get the numerator of f1 of x. So let's just factorise the numerator. Again, we can do the same thing. Let's do the same thing of the denominator. So Menu, Algebra, Factor, and this time we'll get the denominator and factorise the denominator from the fractional tools. So we've factorised both the numerator and the denominator. So you'd think that when a function's numerator is equal to 0, then we will get where it crosses the x-axis. So if we solve that equation equal to 0 for x, we've got x equals -4 or x equals 2. And if I solve when the denominator is equal to 0, that's going to give me where we're going to have vertical asymptotes. However, there's some other special features going on at this point. So let's try to work out f1 of 0. It's actually undefined, and we'd also expect that f1 of -2 is also undefined, and also f1 of 4 is also undefined, because they're my vertical asymptotes. But we're not sure exactly what's happening when x is equal to 0. Let's just try to have a look at the limit here. Let's work out the limit as x is going to approach infinity. We can get the infinity from the pi button. So what would happen as the limit as x approached infinity of this function f1 of x? It's approaching 1. All right, so let's just perhaps try to solve when this function is equal to 1 for x. That tells me x is 0, but x equals 0 was not defined for the original function, so something strange is going on here. All right, so what is actually going on is that, let me show you the graph that I've prepared earlier. That was the question. So this is a nice little visual here of what's going on for the graph. We've got y equals 1 as a horizontal asymptote, but the point x equals 0, 1 is actually a point of discontinuity in this situation. It's not a graph on the point. It is possible, remember, for graphs to cross horizontal asymptotes, but in this particular case it doesn't because it's a point of discontinuity. All right, so in summary for this question, the function has a horizontal asymptote at y equals 1, vertical asymptotes at x equals -2 and x equals 4. The function crosses the x-axis at x equals 2 and x equals -4, and the point 0, 1 is a discontinuity point. All right, so that's a nice little feature there. Let's have a look at another question. This one is probably not one we'd expect to do by hand, but I've just thrown it in to show you, again, two of the features that we actually can use here. So if we wanted to express something really nasty like this in partial fractions, and you weren't sure how to do the partial fractions of it, let's see what's happening. Now, to save typing this in now, I've actually got this one done. Okay, so let's look at what's happening. If I define that function, now this is not done on a notes page, we can factor and get the denominator, like I showed you that one before. So the denominator factorised into x minus 3 squared, x squared plus 9. So here in this situation, we have what's called a non-repeated linear factor, and here we've got a non-linear factor. That was a repeated linear factor. So if you wanted the partial fractions decomposition of this one, now this is a strange one. To get the partial fractions, you actually go expand. I wouldn't think expand puts it into partial fractions, but it actually does. So you can see it's ax plus b over x squared plus 9, plus a c over x minus 3, plus another d over x minus 3 all squared. So that's my partial fractions decomposition. Expand gives me my partial fractions decomposition, and then we can easily just integrate that nasty looking expression. As I said, it's a very complicated integral, but it can show you how the CAS can actually give us the partial fractions equivalence there by using expand. All right, a couple of other little questions here. Let's have a complex number and try to find both the modulus and the principal argument. Now, the principal argument is just the polar angle in this situation. All right, so let's try this one on a notes page, just for fun. Okay, so A, although the complex number is called A, I won't use the value of A. I will actually store this complex number in a maths box. I'll call it Z is assigned equal to -1 minus root 3i. So we'll get the square root of 3, and we'll multiply that by I. Now you must have the multiply I here, and remember, if you're doing complex numbers, you must choose the I from this pi button. We always tell students, the students always say, mine's not working, mine's not working. That's because they've used this I. You have to use the complex number I. Well, you tell them, but they never listen. All right, now the question that we had to do was 1 over the conjugate to the power of 7. So if we look at the menu button now and go to calculations and go to number, there's a lot of complex number tools that we can get here. We can get lots of them here. Convert to polar, imaginary part, real part, etc. Okay, so let me, in this maths box, first of all, have a template for the modulus of the complex number. So we'll get that one again, menu, calculations, number, complex number tools, magnitude. Now that's the same sort of magnitude we do for absolute values. So we wanted the magnitude of 1 over the conjugate of the complex number to the power of 7. So where are we going to get the conjugate from again? The conjugate, menu, calculations, number. Oops. Let's try that again. Menu, calculations, number, complex number tools, complex conjugate, C-O-N-G. So if you can remember that one, and we want the complex number Z to the power of 7. So we'll use the up arrow and 7 there. So that's 1 over 28. All right, now if we want to find the angle or the polar angle or the argument of the complex number, again, it's a similar one. It's complex number, number tools, and this time we're going to the polar angle. And the polar angle, again, I want this same thing. If you want, I can just do a Control-C or a copy and paste it into here and press Enter. So minus 2 pi on 3. Once again, questions like this have been asked in specialist maths exams, multiple choice type questions to find the polar angle. Notice that when we do the polar angle, the complex number is automatically in the argz range, the capital argz range between minus pi less than argz less than or equal to pi. So we're always going to get the complex number in the correct interval there. All right, so let me have a look at the next problem that we're going to look at. That's the older one. So the next problem I'll look at is solving a cubic equation. Now, as we know, the calculator can solve cubic equations. So what we're going to do is we're going to take away some of the cubic equations, or some of the cubic coefficients. So given that z minus 4i is a factor of that cubic equation, now we're told that a and b are real numbers, find the values of a and b, and also we'd like to find all the roots of this equation. All right, so how are we going to approach that one? There are actually 2 methods I can do to solve this question. I'll just do it on a calculator page. So first of all, I'll define P of Z. We're not going to graph it, so we'll call it P of Z equal to Z cubed plus A times Z squared. You must have the A times Z squared. You must have B times Z minus 48. So let's also put that equal to 0, so it's actually an equation. I can actually work out P of 4i. because we were told that z minus 4i is a root. So p of 4i is equal to 0. So that gives me that equation. Now, we saw before we want to solve this for a and b. So what we can actually do is we can extract from the parts here, we can extract just the real part and the imaginary part. So if I just want the real part of that, that's given me that equation. And let's just find the imaginary part of that. If you know them, you can just type them in. So for imaginary, it's imag. And notice it became text there. So again, I'll just press up arrow. That's just going to give me that one. So to solve for a and b, it's then simple. We just go solve, and we'll press the up arrow, and that'll give me my solution for a. Solve for a, and we will solve the other equation for b. That gives me my solution for that one. Now, that's one method of solving that question. There is another method, because we know that if the roots occur in complex conjugate pairs, that z minus 4i is one of the factors. The other factor then is the conjugate of that. So if I expand, I want to expand z minus 4i, and I want to multiply that by the conjugate, which is z plus 4i. So that's one of the factors. Now, we've sort of got to realise that if we look at the original polynomial here, we can see the last term is minus 48. So the 16 has to be what? It has to be a minus 3. So once again, we'll expand that. We need another bracket here. So we've got to multiply that one times z minus 3. And that'll give me z squared minus 3z squared plus 16z minus 48. So therefore we can see that a must equal negative 3 and b must equal 16. And if we want to find all the equations, notice that if I do the solve command of this equation, it won't work, will it? It only gives me the one answer. What I have to do is I have to do C-solve. Then it gives me all the complex numbers as well. All right, so let's have a look at another question here. That's my next question. All right, this is a nice one. Let's try to use the calculator to sketch on an argand diagram all the roots of the equation z to the 6th minus 64 equals 0. All right, so this is a interesting little question here, because we can actually get the calculator to sketch all of these. All right, so what I'll do is I'll open this one up in a new document. All right. So we'll do this one on a notes page as well. So we'll insert a notes page, and we'll define our function. Once again, I have to insert a math box. So I will define my equation f of z, doesn't really matter what we call it, to equal z to the power of 6 minus 64. Okay, so that's done. Now, there's another command. We're familiar with the zeros command, or the C polyroots command, the factor command and the solving equation, but there's another one called the polyroots equation. So if I go menu, calculations, algebra, here we're looking at the polynomial tools, or the solve system of equations. So the one we're after here is the zeros, or the C polyroots. So the C polyroots will be under complex. Okay, so where are we getting the C polyroots from? C zeros. Okay, we don't want that one. We want C polyroots of that expression, and comma Z. Now, the interesting thing here is it puts it all in a list. So let me store all of those again in a list. Okay, so this time we'll store them in a list. Okay, so here we'll go Control, Store, and let's put all of them in, say, the list ZC. So all those complex numbers, the 6 roots, are in the list. What I can then do in another maths box, I can just extract the real components of all of these lists. So I want the real parts of ZC, and I'll store them to, say, REZ. So what that's done, that's just taken off each of the real parts of the 6 elements in that list. Let's do the same thing for the imaginary part. Let's take off the real parts. The imaginary parts. So I'll call them IMZ. So that's taken off all the imaginary parts. Now, if we wanted to see the lists of the solutions in polar form, then what we could do is we could type in ZC, and this time we want to see the roots in polar form. So we'll go Menu, Number, Complex Number Tools, Convert to Polar. So this will give me the list in polar form. Now, the calculator gives e to the I theta. Re to the I theta is equivalent to cis of theta. All right, so all these things are in a list. So what we can do now is we can go to our lists and spreadsheet, and in here, link these to some variables. So let's link these ones to ZC, and they all appear. In this one, we'll link this one to the real part, and this one we will link to the imaginary part. So what we can do now is we can draw a scatter plot of these values. So let's open up a scatter plot, and down the bottom we'll plot on the real axis the real parts, and click over on the horizontal axis over here, we're going to plot the imaginary parts. And there we'll see all 6 roots lying on a circle. We can actually verify it's a circle if we wanted to, but the nice thing about this one is that it's done in a notes page, so that if I just change that to, say, Z to the 8, then we've got some yuckier numbers here. But let's come back to our diagram here, and we get all 8 roots this time. And we can visually see that all of these 8 roots are equally spaced around the circle. They also occur in conjugate pairs as their reflections in the real axis. So some nice little features we can actually do here. Now let me just change that back to a 6 and show you how we can also do that on a graphs page without doing it on a notes page. All right, so let's open up a graphs page here. And this time we're not going to do a function graph. What we're going to do is a graph entry edit. We're going to do a scatter plot. So for the X list, I can just choose from the variable command the real part of Z, and for Y, I can choose the imaginary part of Z. And pressing enter, and we get the 6 roots appearing there. So again, we can do it on the graphs page. We could check then that it's a circle. So let me show you the one I've completed earlier to show you that that is on a circle of radius 2. And we can also show and hide the circle if we want. So show and hide the circle to realize that all 6 roots are appearing on the circle of radius 2. All right, so some nice little visual features there. Perhaps I'll just go to one more, and I've got another one about a velocity time graph, which I'll show you. So we'll do that one later. You can look at that one in your own time, because we don't have much time. All right, let me do the partial. There, let's do this one, implicit differentiation. So find the gradient of the line that is perpendicular to the graph of that relation at the point in the 4th quadrant where x is equal to 2. All right, now again, one of the new features that we can use is this new relation function to sketch the graph of this thing. So I've typed it in there. Notice we have to have the x times the y. So again, if we look at the, on a graphs page, we'd have the relation aspect. So if we went to the graphs page, then hitting the menu and graph entry edit, we see this new one here called relation. So that's going to define rel1. So rel1 x comma y is equal to that expression. So we can actually graph this relation here. Okay. All right, so let's come back to this one. So we'll define it. Define rel1 of x comma y equal to that expression or that equation there. Now, we wanted to find the value of y in the fourth quadrant where x is equal to 2. So we can do that very nicely just by going solve rel1 of 2, so that's x is equal to 2, solving the y value for y, given that, so we'll use the given command, that y is less than 0, because there would be two solutions there. So that tells me the value of y, which is negative 2, when x is equal to 2. Then we actually have to find the gradient. So we're going to use the calculus tool to get the implicit differentiation. Now, once again, implicit differentiation, because I've already typed and defined that expression in, I can just get it from the variable command, rel1 x comma y, and we want to differentiate that implicitly with respect to x and y. So if I wanted to find the gradient of the normal or the line perpendicular to that, that's my gradient of my tangent. All I have to do is to evaluate that when x is equal to 2 and y equal to negative 2, which is the value we just solved up there. So that'll give me the gradient of the normal. All right, so let's go to my graphs page and see if we can graph this relation. Don't know why it's not graphing. We'll go to the one here. So there's the graph of the relation. We can put a point on the graph, which we could move around, and notice that this value here is representing the tangent or the gradient of the tangent at this point. So once again, if I put in x is equal to 2 there, it jumps to the point negative 2. So graphing relations like this, probably not in the course, but I think it's interesting to see the graphs of these relations. All right, the next couple of questions is vector resolutes. You can set these up very, very nicely in a notes page. Again, I'll just show you the one I've prepared earlier. You can store a vector as a 1 by 3 matrix and store the vector B. And the calculator, when it wants a magnitude, the command is norm or unit vector A, and we can easily work out the dot product, getting all of these from the menu for the calculator from the vector symbols, and we can work out everything here. The angle between them. Notice that my calculator is in the radians mode, so I'll have to convert that to DMS. So this is a good little one to have as a notes page to get all your answers. All right, so let's have a look. Let's have a look at this one here. So ABCD is a quadrilateral. PQ, R, and S are the midpoints of the points AD, DC, CB, and AB respectively. Although this is not a full vector proof, we can actually demonstrate this one nicely. Yes, another little feature that I'm doing here is that these files often become sort of quite large with lots of stuff in them. Although I've got one file here with lots of stuff in it, it is probably better to save things as widgets, and then you can just incorporate them into any document. So probably good to watch a webinar about how to install widgets here. Okay, now look at this. I've set this one up, A, B, C, D, as the green quadrilateral. And then I've got the midpoints Q and R and P and S. And I've measured the distance from P to Q and from S to R. So I can move all these points around and we can see that these two distances remain the same, and when I move this point, those two distances remain the same. Although this is not a vector proof as such, I think it is good to sort of just show students what's happening here. All right, so we'll do one more. There's lots of stuff in here. This is an interesting question about a velocity time graph. So an object travels in a straight line relative to an origin O. At a time t seconds, its velocity v meters per second is given by those hybrid, I call them hybrid functions. I think they're actually called piecewise functions now. So we want to find when the object returns to its initial position. Okay, there's a number of ways of doing that. So yes, widgets are very nice things as well. So let me show you interesting ways of doing this one. All right, so we'll open up a new calculator page here and try to do this one. So when we've got hybrid functions, things can go a little bit funny, so it's better probably not to define them as the one original hybrid function. So let me just define g of x as equal to the top function, which was the function minus the square root of 16 minus x minus 10 all squared. And let me define the function f of x as the, no, that was the bottom one. So let me define the function f of x equal to the square root of 9 minus the original t. And although they're t's, we're calling them x's, aren't we? So this is x minus 3 all squared. Okay, so they're the two functions that we've got. So that's my f and that's my g. But they're only defined between t and 6 and 14. So what I'm going to do now is I'm going to define a piecewise function. It's a two-branch, so we'll get it from the template here. Okay, so we'll go into here and we'll define f1 of x equal to, so in here all I've got to type in is f of x because that's defined and give it its domain, and in here we'll type in g of x and its domain was 6 up to 14. Okay, so thinking about this, if we were to look at the graph, this area has got to equal sum of this area. So what's the area just between f of x between 6 and 0? So this time we want to just work out 0 to 6 of f of x dx. So that gives me 9 pi on 2. Okay, now if we think of what these graphs are going to look like, these graphs are very interesting because we've got a positive area here and a negative area here. So if I wanted to solve when that equation to find that value of t, then we have to solve from 6 to t, finding the value of tv when g of x is equal to minus 9 pi on 2. But alternatively, another way of doing this is that I don't even need to work out this value of 9 pi on 2. If I've defined my hybrid function, then I can solve my hybrid function from 0 to the value of tv, where f1 of x is equal to 0. Because what that's doing, that's saying, where is my total area 0? So I've got my area in here and my area in here. We could sort of try to sort of move this point till we match that value up with that area there. So the answer to this one is the value of t when it returns to its initial position is 10.93. 10.39, sorry. So a nice little question there again. All right, now I've got lots of little other documents and questions in this document, but I think I'll hand over to Peter and let him finish off with some other sort of questions in specialist maths. And these files will be available for you to share after the session. So over to you, Peter.
Fantastic, and thank you very much for all that, Ray. If I can retell a story that I know I've told many times before. The last time I was teaching Special Maths, and I had only the one student, and we were working on the input-output mixing problems, and she said, Mr. Lannan, this is obviously a fairly straightforward algorithmic procedure. Surely somebody has written a file or a notes page that'll do this. And I said, yes, you are absolutely right, and what's more, I reckon I know the guy who will have done it. I contacted Ray, and he provided us with a file. He had written it. He provided us with that file, and also this wealth of others. So just a reminder, students are not required to clear their calculators going into exams. So it's an absolute gem to them to have all of Ray's files that you are all going to have as a result of attending this webinar. So thanks, Ray. And Peter, we can see your screen nicely.
Good evening.
We can't hear you. Yep.
Well, if you didn't butt in. So good evening. What students should do when they walk into the exams, they should do some preparation with their handheld or their calculator. So in exam 2, the extended response, generally there's 6 questions in the extended response section, and there's usually 20 multiple choice questions. For the multiple choice questions, you know, some of those will be conceptually based questions whereby students won't need to use technology. There will be other questions, of course, where technology is useful. But I do feel as though that students can do a little bit before they go into the exam. For example, if you think about exam 2 as being 6 questions in extended response, then I think it might be a good idea for students to have what's called 6 problems already positioned on their handheld, with the view to minimising the possibility of mucking up a question due to variable mismanagement. So what I've got here is a file which says SM, Specialist Maths Exam 2, ER blank, and basically here the second digit, that represents a page number, and the first digit here represents a problem number. So this is 1.1, and it happens to be a calculator page. I've got a second page in this problem, 1.2, happens to be a graph page, and then so on and so forth, 2.1, 2.2, 3.1, 3.2, 4.1, 4.2, 5.1, 5.2. So to show you how to insert a problem and to give you a brief demo of why I think a one-to-one correspondence between exam question and problem is so useful, is if we go to Doc and then number 4 for insert, and if you notice up the top of the commands there, you can either insert a problem or a page. Now if we insert a problem and then add a calculator, here this is page 1 of problem 6. So I think that the students that are doing extended response, when they're answering question 6 in the exam, they should be in problem 6 of their handheld or their calculator. So for example, if in problem 6 we've got f of x, and we can assign that by pressing control symbols template as something like, let's press trig, and then go across and down and choose inverse cos, and then say 2 on x, and then press enter. So we have defined a function, and it might be a 1-mark question to start off. It might say, you know, what's the implied domain or maximal domain of f? So what you could do then is, well, students are very likely to just type in the word domain from the non-QWERTY keyboard down the bottom of the handheld. Domain, as Raymond showed you, press the catalogue button. It's denoted by an open book icon. And then, I don't know how good a tactic this is. If I press the E, takes me down to the E's. Not too bad. Scroll up to highlight domain. press enter, and then domain, f of x, comma, the independent variable, press enter, and there's the maximal domain of f. Now, in problem 6, f of x is recognized as being that inverse trig function. If we went, for example, to problem 5 and we typed in f of x and press enter, what it does is it spits back f of x. So in other words, what we're doing is well, in Donald Trump's language, we're building a great wall between each of the problems. So problem 1 is question 1, problem 2 is question 2, and there's a fence or a wall. So the problems are separate. So the variables that are assigned or defined or stored in one problem are not in another problem. And I think that is quite sage calculator management that the students can employ before they go into their exam. I think it's a good idea for their students to have a vision of what their calculator might look like at the end of the exam. So if we just go back here, the next thing I want to just briefly talk about, it was alluded to in the chat window by Brian and also mentioned by Raymond, is this idea of a widget. So it's not an insect or a disease. If you look up widgets on Google, TI-Nspire Widgets, and then click on widgets, one nice feature here as well is that now that there's sort of like an e-guide that would accompany the PDF version of the guidebook, and it describes a widget as a TNS document that is stored in your My Widgets folder. And you can use widgets to easily access text files, to insert and run scripts such as preloaded widgets. Now, if you've not made a widget before, you will, and you're on the latest operating system, you will have access to the stopwatch, which is not all that useful, I suppose, for the specialist maths students. But what you can do and what the students can do is build up a huge number of widgets which you can students can take into the exam and hopefully use judiciously to answer various questions. My sort of feeling about exam 2 is with a pretty decent suite of widgets, students, the students that are sort of strugglers tend to get the most boost. You could probably add, 10 to 12, possibly even more marks to a student's score with, a good suite of widgets. So it's definitely worthwhile investigating. The important thing about a widget is that the TI-Nspire extracts only the first page of the selected TNS file and inserts that into your open document. So that's worthwhile paying very careful attention to. So when you're making a widget, make it one page. I think that's very, very important advice. Just clicking on here, creating a widget. So widgets is a document that's regarded as a widget when it's saved or copied to the designated My Widgets folder. So for the students handheld, the default location is My Widgets, and it's also the same for the software. And again, there's this caveat that when you add a widget, TI-Nspire extracts only the first page. So what I might do to finish off is show you how to make a very basic widget, show you how to save it, and then show you how to call it up in an open document. I might have time to do a pre-prepared widget on stats. We'll just see what transpires. So I'll go to this document 1 here, And now this document I'm hoping is a notes page. I just want to check. No, it's not. So what I'm going to do is I'm going to insert another document, and I'm going to start off with a notes page. All right, so we're going to start off with a notes page. And if we go to document 2, okay. So the thing about a notes page is you can write some text. So we will write some text. We might go VOSOR about x-axis. All right, so let's look at volumes of solids of revolution about the x-axis. Now, notes pages are interactive and dynamic, and the main object that's a central feature of a notes page is a maths box. And so if we press menu and then 3 for insert and then number 1 or enter for math box, notice that there's a shortcut as well, Control M, which I'll possibly end up using. So there's 2 ways of accessing a math box, through the menu or through the shortcut Control M. And so what I'll do is I'll start off by assigning the lower limit A, control symbols template. I'll assign that to be 0, an arbitrary value, and press enter. Notice that the input is in blue and the output in this instance is in green. You can change the appearance of these math boxes. For widgets, I think it's really important that the students see the input and the output. You can, for example, if I click in here and press Control menu, math box attributes, you can do all sorts of things. You know, you can hide the input, you can hide the output, etc., etc. So show input and cancel there. I think it's a really good idea to show the input and to show the output. So in this next math box down here, now I know that I'm in a math box because we're inside a box and there's also that red dotted border as well. It's important that students and yourselves, you realise where you are. For example, if I go 1 to the left, I'm outside the math box. I go 1 to the right, I'm inside the math box. So we'll assign B, control symbols template, we'll assign that to be 1. So we've got our lower limit and our upper limit. Now the next thing we want to do is we want a function. So we'll have f of x and with control symbols template. So the assign command is colon equals. It works like define. So if you want to continue using define, that's fine as well. Notice that equals is not a good idea. All right. So if you're using the assign command, it's colon equals. So we'll choose 2 times e to the 2x. Notice that I pressed the e to the x button. Don't use letter e. Press enter. If that's a complicated function, it really should be a little bit more judgmental and say well done. But anyway, that's it's a simple exponential, so done will suffice. Then in this next math box which is opened up, what we can do is we can assign volume. We can assign volume, control symbols template, to be pi. So I've typed in pi as Raymond adroitly showed you earlier, multiplied by. Now, if you press Shift plus, that's the template for the definite integral. So that's quite handy to know. For the derivative, you wouldn't believe it, it's Shift minus. It's sort of mirroring the, you know, the power rule of differentiation, the power rule of integration, you know, for x to the n. So we have a lower limit here of a, and then an upper limit there of b, and then what we want is we want f of x all squared dx. So hopefully I've typed that in right. All these people are sending messages about the football, and so it's very hard to concentrate. So if you press enter there, what that gives you is that gives you the exact volume. There might be situations whereby you need a volume which is expressed to a certain number of significant figures or decimal places, what you could do is you could build in a feature where you have an exact answer and also an approximate answer. There is an approximate command in the catalogue. You could type in the APP ROX as well. That's the one I'm after, so approx. And then if we press var, and we can call up vol, press enter, enter, okay? So that gives you an approximate volume. So what would be required now is we can say that this is going to be our widget to find a volume of solid of revolution about the x-axis, and we could now go about saving it as a widget. So if you press doc and then 1 or enter for file, and then I'm going to choose 5 for save as, and then what I'm going to do is my documents, and then I'm going to head down to finding my widgets, and then click on that. And if you have students that do 2 subjects, for example, methods and specialist, or further and methods, it's a good idea to have a system set up for your file names. Now, I haven't thought about this too deeply, and you might be able to run with the idea that I espouse here. But if it's a specialist maths widget, you could start off with the SM, and then, for example, volume of solid of revolution. If, for example, you were making one about the average value of a function, and you know that that's in methods, that widget could be called AVLength, you know, something like that. Or what I've even got here, well, we'll show you when we call up the widget. So the file name is smvosor, and we press save. Okay, so I've saved that as a widget. Now let's go back into this exam 2 document that I had, and in question 1, the students need to find a volume of solid of revolution, and we say, well, okay, what we can do is now let's show you how to add the widget to an existing document. So what we do is we press doc, and then number 4 for insert, and then A for widget, and what should come up is a list of all your widgets. Now, notice that that one there, that's for further maths, that's an arithmetic sequence one, and notice that I've got a couple of SM ones there. The stopwatch is one that you should all have, that's the inbuilt one. So we say, okay, SMVOSOR, that's the one we want to add, and we add it, and it's ready to go. And so what you can do now is you can change some values. So let's have, that's 1, that's 2. So you're not making these widgets, you're not making them in the exam. They're already made, all right? And so what you do here is I've been clicking on them. I've been going into each maths box and pressing enter to activate them, and to also specify values, for example, for the lower limit, the upper limit. Notice that I edited the function there for f of x, etc., etc. So your widgets is your one-stop shop. They're all one page, and as I said, building up a really good suite of them, students should really get a seriously good boost to their score by having access to them. Of course, there's still intellectual work involved in the exam, and formulation is still important, and interpretation is still very important. But as I said, for the more mechanical style questions, it's useful. It's a nice Linus's blanket, particularly for the the battlers. So the final thing is I'll go to another. So okay, so I'm in problem 2 now, and I've got this question to deal with. Well, first of all, let's have a look at here's the question that I would like to look at just in a couple of minutes. So I'll probably end up, Brian, finishing probably at about 3 or 4 minutes past 8, just to give you a heads up. So the weights of oranges produced by a farm can be modelled by a normal distribution, the mean of 205 grams and a standard deviation of 10. The farm also produces what you'll find is very, very consistent lemons with the modelled by a normal distribution with a mean of 75 and a standard deviation of 3. And this is where conceptual work and interpretive work is still required. Find the probability that the weight of a randomly chosen orange is more than 3 times the weight of a randomly chosen lemon. So what this is tapping into is linear combinations of independent normal random variables. So if we let, in general, x and y be independent normal random variables and a and b are constants, then what you'll find is that random variable ax plus by is also normally distributed. And since x and y are independent, it can be shown via expectation algebra that e of ax plus by equals ae of x plus be of y, and var, or the variance of ax plus by, can be written as a squared var of x plus b squared var of y. Intuitively, it makes sense that you've got a squared and b squared there, because variance is non-negative, so it would be silly to have a's and b's there, particularly when b can be negative. So it's like the students and professors question here, this one. So what we get here is we want to find the probability that the weight of a randomly chosen orange is more than 3 times the weight of a randomly chosen lemon. And so our required probability is we require, if we've got random variable capital O representing the weight of a random orange and random variable capital L representing the weight of a lemon, we actually want to find the probability that O is greater than 3L. And what you need to do is, I think it's sensible to set it to an inequality with 0 on the right-hand side, so subtracting 3L from both sides, so the probability of O minus 3L is greater than 0. And the linear combination is if we let W equal O minus 3L, then basically what we're finding is the probability that W is greater than 0. And the interpretive work is to have an idea about what the correct mean and the correct standard deviation or variance is going to be of that linear combination. So here we've got E of W is E of O minus 3L. We know from expectation algebra we can write that as E of O minus E of 3L. The 3 comes out the front. So basically it's E of O minus 3E of L. So you can see there that A equals 1 and B equals negative 3. And for the variance of O minus 3L, and applying expectation algebra again, there's a 1 squared written there, although it's it's invisible. There's a 1 squared, so it's the variance of O plus 3 squared times the variance of L. So what we want to do is, we've been given this question to answer in the exam. So what we do is we go to our blank document here and we say, okay, it's time to get my linear combination of 2 normal variable widget out. So what you do is you press doc, 4 for insert, and then A for widget, and then you go down and you find, this is my linear combination of 2 independent random variable widget, and I add it. And so what we do is we now go to, so there's a definition, nearly finished, Brian. It's just a matter of filling in these math boxes. Now, the mean for the oranges was 205, so we'll put that in there. The mean weight for the lemons was 75, so put that in there. Now the variance, so we got told the standard deviation was 10, so the variance is 10 squared for oranges. For lemons, the standard deviation was 3, so 3 squared for the variance. And so all I'm doing is just going into each math box and just entering the value and clicking. A was 1, remember. B was -3, remember. Now I've set up a math box which will automatically calculate the new mean for us using the values for the two means and those constants A and B. And we get a new mean. So in other words, E of W is -20. The new standard deviation, the reason why it's standard deviation is because when you enter your last entry for the normal CDF, standard deviation is required. So we press enter. So the new standard deviation is the square root of 181. We required the probability of W being greater than 0. So the lower value in this instance is 0. The upper value is infinity. Now, you can type in infinity. Very nice. And then in this last math box here, the probability is being assigned to be the normal CDF of lower value, upper value, new mean, new standard deviation. Press enter, and therefore the probability that W is greater than 0 is that. In other words, the probability of a randomly chosen orange being weighing 3 times more than a lemon, randomly chosen lemon, is that. Over to you, Brian. Thank you.
Thanks, Peter. And we saw your apologies there for going over time there as you did. I will close this out fairly quickly. Try that screen share again. So thank you once again to both our panellists this evening. That was Peter Flynn.
Thank you, Brian.
And Ray Rosen.
Thank you, Brian.
And people have been asking and hoping for the copies of your files. A reminder that you do get an email following this event. You will receive in that your PD certificate and a link to where you can download the files. But why stop there? You can go to the Webinars on Demand website. You can watch any of the past webinars, either through the TI Australia website or through our YouTube channel. The link's on your screen now. And also with the on-demand webinars, I think you can also chase up the associated files, so that can be useful. I thoroughly recommend that you arm your students with these very useful files for their exams. As you know, they're allowed to take these into their exams and draw upon them as they proceed through exam 2. So it's a good night to all. Thank you once again to our presenters, and farewell.